Good evening. This is Mr. Marek. It is currently Wednesday, September 9th, 2015. It's about 6 o'clock in the evening. I'm currently sitting on my couch watching a thunderstorm outside. And of course, that gets me thinking about thermodynamics. Thermodynamics in physics is the study of motion and energy at the microscopic level. And so if you're currently watching a thunderstorm like I am, I'm sure you're thinking about the same thing. If not, then you probably need to grab your physics notebook and follow me as we learn a little bit about motion and energy at the microscopic level. So the beginning part of this should be basically a review. I'm going to kind of title this the kinetic model of matter. Remember what kinetic means. And we're just going to start out by kind of reviewing a few simple things to make sure we're all on the same page. For example, I'm sure you remember from chemistry that all matter is made up of really, really tiny particles called atoms. Don't write that down if you already know it. And I'm sure you remember that atoms are things that can't be divided into anything simpler while still retaining its properties. For instance, if you try to divide an iron atom, it's no longer going to have the properties of being iron. It's going to be something weird and exciting we'll learn about later on this year. Compounds are made up of several atoms which are held together. Sometimes call those chemical bonds, but really they're electric forces. For example, water. I'm sure you remember that from chemistry as well. So here's where the new stuff begins. I'm sure you've been wondering, since you first heard the word, how do we know what atoms are? How do we know what their properties are and that they even exist? So one of the first really good, rigorous proof that atoms exist was given by a guy by the name of Albert Einstein. He was able to use the atomic theory, that atoms are what make up matter, to explain a phenomenon called Brownian motion. Basically, what Brownian motion is if you drop really tiny little pollen particles into water, they kind of make little zigzag patterns as they move through it. They don't move in just a straight line. Einstein was able to explain this by assuming that water was made up of little tiny particles just like the pollen was. And so what he did was he showed that if atoms really existed, if water was made out of little particles, then the distance between the zigs in the zigzag motion depended on the temperature of the water. Let's investigate that further. So here's the microscopic view. The motion of a particle, i.e. The pollen in this case, in water kind of looks like this. Moves a little bit, then it zigs, moves a little bit more, zigs, moves a little bit more, zags, moves a little bit more. In order to really see this, you kind of need a microscope. Otherwise, it kind of just looks like it's gradually spreading throughout the water. And so what Einstein did was he proposed that the particles, in this case the molecules of water, were responsible for redirecting the particles of pollen. Kind of like this. They pushed it and it moved one way, and then those water particles ran into the pollen and pushed it a different way, so on and so forth. So basically he assumed that those pollen particles were moving through a sea of water particles. Those water particles would be comprised of atoms. He predicted, using the atomic theory, that the distance between the zigs would decrease when the water got hotter. And so the motion would look like shorter distances between zigs and zags. This was later confirmed by experiment. So Einstein was really good about not only proposing what theory should say, but also giving us a direct way to test it later on. So here's what the motion looks like in hot water. It moves a shorter distance before zigging and zagging. So the big question, it's kind of a question I'm going to pose to you right now, is what does this tell us about the atoms or molecules whatever you want to call them, that make up, in this case, water. So press pause on this for just a second and write down things that you can think of that you can claim based on this little evidence, thought experiment, whatever. Don't skip the trivial stuff. So don't assume anything right now. Just write down something that you can claim based on this idea. So here are some things that we can learn from this. First of all, the water particles change the motion of something, namely the pollen, which shows that they exert forces on stuff. Now, as far as we know, the only things that are capable of exerting forces are things with mass. So this tells us that those little particles have mass. They're moving around, so things that are moving with mass have momentum, and they also have kinetic energy, which are really important properties of matter that we already know and love. Hopefully these were kind of obvious. Maybe they were so obvious that you didn't even really think that they were worth mentioning, but it's a really good place to start. So here are some of the less obvious things. First of all, there's empty space between those water particles, as evidenced by the fact the pollen is actually able to move a distance before it's redirected by other water molecules. Next, those particles gained momentum and energy when the water was heated. The hot water caused the pollen to move around more, zigzag after traveling a less distance, which means that there was an increase in the rate of collisions between the water particles and the pollen particles. This increase in momentum and energy couldn't have come from mass, because hot water doesn't start to weigh more, so it must have come from increased velocity. And then the last thing is that the motion is completely random. Those particles move in no discernible order. They're not all going the same direction. They're going all different direction. So the motion is random. So we can kind of put some of these observations together and we can build a simple model to help us understand and describe the motion, forces, energy, and momentum of microscopic particles. The stuff that makes up stuff, in other words. We're going to make a couple of simplifying assumptions so that we're all speaking the same language and that we don't try to overcomplicate things at the very beginning. The first thing that we're going to do is we're going to assume that the particles, atoms, molecules, whatever, behave as hard spheres which collide elastically. Remember, elastically means that there's no energy lost. In this case, that's going to be true because there's nowhere for the energy to go. We can't blame it on anything else. It's not going to go anywhere. It's got to be conserved. Secondly, when the particles are not colliding with each other, they travel in straight lines at constant velocity. Basically, that means that Newton's laws are obeyed. The only thing that can change the motion of those things are forces, and those forces come during a collision with something. Third assumption, motion is random, kind of like we just said, and that there's a variety of different velocities, meaning they're all going different directions with different speeds. And then fourth, we're going to start out only by discussing gases. And what makes a gas is the fact that the particles don't exert forces on each other. We refer to such a gas as being an ideal gas. In chemistry, you may learn about gas reactions. We're going to assume that that kind of stuff's not taking place. Like I said, keep it simple at the beginning. So here's a real simple picture of what a gas would look like to help us understand. Here's a container. Remember, gases are going to fill their container. There's lots of empty space. There are all the particles. And they're moving at random. And so notice a few things about those arrows. There's a variety of different speeds. They're going a variety of directions. And that there's no real order to the direction that they're moving. They're not all going one direction. They're going in all directions at once. and then they don't interact with each other. And so the only way that they are going to ever know that each other are there is when they run into each other. So there's no forces between them. So how are the speeds distributed? How can we describe what's going on with those velocities? So notice, first of all, that some of the particles move slow, a few of them move fast, but most fall somewhere in between. So there's a slow one. This guy's going pretty fast. But most of them are falling somewhere in between the extremes of slow and fast. Not all of them are going to get highlighted, but most of them are going to get highlighted. So those are all the ones that are kind of sort of falling in between the extremes. So, due to the collisions between the particles, the faster particles tend to slow down, and the slow particles tend to speed up. So no one particle, like for instance, this guy right here, is going to be able to go really fast for very long because it's going to run into something that's going to slow it down. What this does is it tends to make the speeds be clustered around some average. So not too many slow, not too many fast, but most of them somewhere in the middle. So the way that we can visualize this is with the graph. On the x-axis, we're going to put the speeds of the particles, and on the y-axis, we're going to put the number of particles that have that particular speed. And so when we graph it, it looks something like that. Well, there's very few slow particles. The left end would be slow. Very few fast particles. The right end would be fast. Most of them are somewhere in the middle. The peak of the graph would be called the most probable speed, meaning that if you were to go through and count all the particles and then figure out each particle's velocity, most of them would fall at that velocity, whatever it might be down there. This distribution of speeds is referred to as the Maxwell Distribution, named after a guy named James Clerk Maxwell, who predicted this distribution by doing a lot of really complicated statistical analysis that you're going to have to learn someday when you're in college. It will probably make you cry. I know it made me cry. So, what happens if we take those particles and on average speed them up? So there's my particles again. If we speed them up, then on average they're going to be going faster. Something like that. Notice that on average the arrows are longer than they were before. The speeds are still going to be clustered around an average. So notice that there's still a medium ground that most of the particles are at. Not too fast, not too slow. And so if our graph used to look like this, the new graph will look something like that, where the peak is shifted over to the right and the width of the graph is increased. So that's the high average speed graph that we just drew. So notice the most probable speed has been shifted over, so on average they're going faster. There's more faster particles, and notice that there's a greater range of speeds. In other words, there's more chaos. There's a lot more randomness in the motion. And so there's not as many going slow as there were before. The average has been shifted to the right, so on average they're going faster, but there's not as many going any particular speed. That's going to be really important later on to us when we try to understand the idea of entropy. So if you know that word already from chemistry or something, you might kind of think about how that word applies to that distribution graph. Okay, so we kind of know what the velocity of the particles are doing. What we want to try to do next is use that to explain the pressure caused by a gas. Gases exert pressure on their container, or whatever they're in contact with, due to collisions with the sides. They're constantly moving, and so they're constantly running into whatever is trying to hold them in. So here's a real simple picture. Here's the wall of our container, or whatever we put in the gas. So you could consider this to be your skin, your eyeball, whatever. And then here is a gas particle. So mass m, some velocity v. It's going to run into the side. When it runs into the side, the wall is going to push it. Call that force due to the wall. Newton's law says there has to be a reaction force. So the particle pushes the wall, and then the particle is redirected. And so because its momentum had to change, there had to be a force exerted on it by the wall. The reaction force is from the particle on the wall, and that's what causes the pressure due to the gas. This is for our slow particles. If we look at the faster particles, so maybe this guy is going 2v, when it runs into the wall, there's going to be a larger force on it, meaning there's a larger reaction force on it, because the change in momentum is going to be greater. So we're going from 2v to the right to 2v to the left. That's a greater momentum change than the slow particle, going from v to the right to v to the left. So for a real gas, these collisions are happening literally trillions and trillions of times per nanosecond. Basically, what you feel is a continuous bombardment of these things that causes a continuous force. Force over area is pressure, so that's why the gases are exerting pressure. Higher speed particles cause higher pressure. Because they're going faster, they require more force in order to change directions. If somebody were to ask you to calculate how big that force was, then you would probably use the impulse momentum theorem. F delta t equals delta p. So, how is temperature, which is a measure of how fast those things are going, related to pressure? So, a working definition for right now is that temperature is a measure of the average kinetic energy of those tiny particles. In other words, faster particles have more energy and thus have a higher temperature. So if we go back to the previous slide, the picture on the right would represent something that's got a higher temperature. So that would represent a hotter sample of gas in the picture on the left. Higher speed particles cause higher pressure because they're running into the walls more often and with more force required to redirect them. And so thus we conclude that temperature and pressure are directly proportional to each other. If you wanted to write it real fancy, you could write it like that. P is proportional to T. Capital T is going to be our symbol for temperature, by the way. This is often referred to as Gay-Lussac's law. That would be a Frenchman who kind of wrote the law down. It's kind of sort of common sense. If you've ever heated up a closed container, for example a baked potato in the microwave, you know that the pressure will quickly increase, oftentimes causing an explosion. And so if you've ever tried to cook a baked potato in the microwave without poking holes in it to release the hot gas, and then you've had to clean up the microwave afterwards, you kind of instinctively know that. Temperature increases with pressure. So the reason that temperature and pressure are important is that they are macroscopic properties that we can actually measure. You use a pressure gauge to measure pressures, you use a thermometer to measure temperature, and so those are things we can actually measure. So we'll refer to those as macroscopic or big scale properties that we can measure and understand. But what we need to be able to do is understand what causes those things and their properties based on the microscopic picture. And so that's what the kinetic model allows us to do. And so understanding those assumptions, so those are those four assumptions. understanding the difference between a low temperature gas and a high temperature gas, understanding how the speeds are distributed, and understanding how pressure is caused by collisions with the side of the container or whatever is in it are going to be real important to understanding, too fast, the relationships between pressure, temperature, and later on volume that we need to learn in order to understand how we can use all this energy to do work. That's kind of the end goal here. How can we take all of that energy of these things moving around real fast and use them to do work? That happens every day in your car engine. We want to be able to explain it. But I think we've gone on long enough for now, so we're going to call this the end. And we're going to be learning lots more as we go. So make sure you stay up to date on what's going on so that you don't get too far behind. Till next time, bye-bye.